Okay, last class we stopped right here. That's the previous slide actually. We proved that the stress tensor is symmetric, and we also showed that there are 6 independent components, and we also figured out how to find the signs of the stress components. So today we'll see how to calculate in 2D and later 3D, how to find the eigenvectors and eigenvalues. What are these eigenvectors and eigenvalues? Eigenvector corresponds to the direction of principal stresses, and eigenvalues correspond to the principal values themselves. Okay, so first let's introduce that concept. One second. This is lecture 10, right? Oh, so first I want to write eigenvalues are equivalent to principal stress values here, and eigenvectors are equivalent to uh, directions of principal directions of principal stresses. Okay, so in 2D we can easily find what are the principal values and principal directions based upon this formula. You might have seen the derivation of this formula back in your second year solid mechanics course. Here we are going to take it for granted. Sigma, first let's suppose that x and y are the axis in the original coordinate axis, and let's now imagine a new direction at an angle theta in the anticlockwise direction with respect to x-axis, the new axis. And if you assume the new axis is x prime and y prime, okay, I draw it here. Sorry, this is x-axis, original x-axis, which should be the y-axis. And if we rotate it in the new direction, we have x prime and y prime axis. On this new axis, we want to figure out what are the stresses and new stress components in this new direction. So just like vector, we have seen last class that the rotation of the axis does not change the vector. In the same way, the stress tensor remains the same. So let's assume this is a 2D stress tensor. In the original axis, we have the components sigma xx, sigma xy, and then we have tau xy components. But in the new axis system, we will have completely new components. We will have x prime, sigma y prime, tau x prime, y prime. So these are the new components. We want to find the new components in terms of old components. So if you take these components, these are all known, and the angle theta is known. How do we find the new components? Here we can see we have three components which are unknown: sigma x prime, y prime, and tau x prime, y prime. So how do I find in the new direction? This is the x prime direction, and 90 degrees to it is the y prime direction. How do I find it? This is the relationship for that. Here we have it is written with a single subscript, but this refers to your normal stress component sigma xx component in the original coordinate axis, sigma yy, and then we have tau xy and the angle phi. Okay, so instead of theta, we write it as angle phi. Okay. So here we are given only one normal stress. The normal stress is along x prime direction. So this is the sigma x prime value. How do I obtain in the y prime direction? What is the component? We also need this. So how do I obtain it? Very simple. We take this same formula, replace the angle phi with phi plus 90. So you can see this is angle phi. You want in the new direction y prime. How do I get it? I consider the total angle, which is the phi plus 90 degrees. Okay. So we have originally x prime. Now, if you want y prime, just rewrite the formula. 2 plus sigma x, sigma y over 2, and cosine 2 times phi plus 90. Then we want tau x, we have a term tau xy, so we need to add that as well. Sine 2 times phi plus 90. Okay, so this will be the sigma y prime, sigma x prime, and tau x prime y prime. Okay, so for tau x prime y prime, we need not change anything. Phi will stay as phi, and this is the equation. How do I find the maximum principal stress? Direction. It is maximum when sigma assumes the maximum and minimum value. So if I differentiate this this particular equation, what is it I am going to get? With respect to angle phi, that is what I am going to do. So rather I put a partial here, differential. The first term here will disappear. If I differentiate, the second term will give, forget phi plus 90, assume there is only the angle phi here. Then what you are going to get? Cosine, differentiating cosine term will give me negative 2 times 2, then sine 2 phi. Okay, The next one, I will get positive 2 times tau xy cosine 2 phi. And this should be equated to 0, identically equal to 0, because to get the maximum and minimum, the first differential should lead to a 0 value. Okay, so solving this, what we are going to get, keep this, take the sine phi term to the other side of 0 on the right hand side, and then solve it. We can cancel off 2 terms here, and we are going to get tan 2 phi. Okay, and this is the principal direction, so we can write phi p for principal direction should be equal to tau xy over sigma x minus sigma y over 2. So this is the formula for principal stress direction. And you can see the same formula here. If you want the principal values, then we take this and substitute in the cosine and sine directions. So how do I get what is the cosine of the values? I know tan 2 phi p. Cosine can be easily obtained by writing it as a triangle. Here, I'm going to represent it in the triangular form. The opposite side is tau xy, and this angle is 2 times phi p. Notice that the angle is 2 times phi p. The original angle here is phi, but when we go for the formula, all the angles are substituted 2 times angle phi. So the adjacent side is y over 2. So here it is xx and y. So how do I get the hypotenuse here? I have the opposite side, the adjacent side, hypotenuse is square root of, use Pythagoras theorem, and we can write this term okay. So now we can get the cosine of the angle. Cosine 2 phi p along the principal stress direction will be equal to, so let's call this r on the hypotenuse, and I'm going to write the cosine of the angle over 2 divided by r. Then we can also get sine of 2 phi p. We get tau xy over r. Take these values, substitute back into the equations originally here, and you will see that you are going to get this formula back. Okay, exactly this formula you will get. You have the first term, and the second and the third term, when you look for it, when you substitute for it, cosine 2p, we will get finally this formula. So let's check it by substituting here. If we get the same formula, x prime should be equal to plus we're going to use over 2 multiplied by cosine of the angle 2 phi. So this is the formula. So let's see here. Cosine of the angle consists in the numerator of this part. So if you do that, actually, you are going to get the square of this term and divided by r. Wait a second. The r term, we are going to just keep it as r for simplicity. And then we have tau xy term sine 2 phi. And then we will get square over r. Carefully take a look. Here we can rewrite x prime sigma xx plus sigma yy over 2. This term will remain the same. On the numerator, you can clearly see this term. What is r? If you take a look at r has this square term plus tau xy square term. And in the numerator, you can see square term plus tau xy square, and the numerator is nothing but r square, taking these two terms together. In the square bracket, the numerator is nothing but r square. In the denominator, we have r. So that means we are left with r here. R square over r gives you r. And what is r? The square root of this term. And exactly that is what we get. Okay, plus term. So along the x direction, we realize from this formula, along the x direction, the formula is plus the term with the plus quantity. Okay, yeah. So this is along the x direction. What is it along the y direction? It should be obviously the term with a negative sign. Minus r. You can check this very easily. Let's go to the formula for sigma y prime. Here we have cosine of 2 phi plus 90 within the bracket. If you expand that, you can write it as cosine 2 phi plus 180. 180 is nothing but pi. And what is this value? If you remember, we are going to use, this is the positive first quadrant with 0 degrees, 90 degrees here, then 90 degrees, or let's write it as pi over 2. And in this direction, we are going to write pi and 3 pi over 2. You can write all silver T cups. So you can remember in that way all angles, sine and the inverse of sine, the reciprocal of sine, tan and reciprocal of tan, which is cot, cosine and reciprocal of cosine. So in each of these quadrants, if our angle lies within any of these quadrants, then we can decide based upon the sine or cosine formula whether it is positive or negative. We can take this particular angle. So we are on the third quadrant, phi plus 2 phi. We are inside this quadrant, and it would have stayed positive the cosine of this angle would have stayed positive if C existed here. But cosine angles are not positive in the third quadrant. That means this should be negative cosine 2 phi. So we can see the sign just changes, that's all. So we will get a minus value here. We can also take a look at sine of the angle, sine here, and sine of that angle will also give us a negative value. So again, sine 2 phi plus phi will give us minus 2 sine 2 phi. Okay, so we get a negative r value. Okay, so we have derived what are the principal values, and you know that the positive quantity is along the x prime direction at an angle phi, and the negative value is along the y prime direction. What about the maximum shear stress direction? We can get the maximum shear stress direction by simply differentiating this equation and equating it to 0. But along the maximum principal stress direction, we can also calculate what is the shear stress. And if you calculate it, you are going to find that it gives you a 0 value of shear stress. First, let's see along the principal stress direction, what is the tau x prime y prime value along the principal stress direction. We can take this formula, substitute 6yy, and then multiply by sine 2 phi. Sine 2 phi is nothing but, according to the formula what we have seen, tau xy over r. Take the second term, we have tau xy times cosine 2 phi. And cosine 2 phi, we have already seen the formula. We have this formula. Okay. 2 and divided by r, so in the denominator we will also have r. So we can see these two terms cancel each other and we get identically equal to 0. So along the principal stress direction, what we are seeing here is this is the formula we get. Principal stresses. We have sigma 1 or equal to sigma x prime, sigma 2 or sigma y prime, and the shear stress values are 0. So along the principal stress direction, this is the case always. So this is the case for 2D. What about 3D? In the case of 3D problems, we will have the principal stress tensor as follows. You will have all the shear stress components as 0. Okay, and you will have the minimum and the maximum values of stresses along the diagonal. So you will have only normal stresses along the diagonal, and it will be the minimum and the maximum values. Similar to your 2D, the maximum and the minimum value. In the same way, you will have maximum, minimum value, and an intermediate value. In general, the principal stresses are arranged in this way. Unless 2 of the principal stresses value are equal or 3 of them are equal. In that case, it doesn't matter, but in general, sigma 1 is the highest value, 2 intermediate, sigma 3 lowest value. How do we find principal stresses in 3D. So in 3D, we have to find what is called as eigenvalues. Your principal stresses are nothing but eigenvalues. It's not easy to solve a cubic equation and get eigenvalues directly. So what do we do? In such cases, we have to use a software like MATLAB and get eigenvalues. Okay. How about the principal stress directions? Principal stress directions are obtained from eigenvectors. Eigenvectors in 3D. Here 3D. Okay. How did we get directions in 2D case? It's very easy. In 2D case, we just get the angle phi. In 3D, we will need 3 different angles. Okay, so this is for 2D. For 3D, we need 3 angles for the direction. So instead of obtaining 3 angles for the direction, what we are going to do is directly get the vector. Direction unit vector along the directions. For example, if I want to know what is the direction along x prime axis, I will get what is the unit vector along this guy, and let's call this as I prime. The unit vector along I prime can be expressed with the help of components of x unit vector. Let's call this x I. Unit vector along y as j cap and j cap. I prime can be obtained in terms of I cap and j cap. And in the same way, we can obtain the directions, particular directions in 3D in terms of ij, I cap, j cap, and k cap values. Okay, so let's see a simple example here using MATLAB. I'm going to create some random matrix, and let us assume this is the stress tensor. Okay, I'm going to assume A is the stress tensor. Okay, so let's assume okay, so it won't come out symmetric, so I'm going to make it the stress tensor symmetric from these values and enter it there. 92, 28, and let's say here the second value should be 92, 64, and 55, 28, 96. Okay, so this is the stress tensor I'm going to consider. It is symmetric, and I want to find the principal stresses and directions for this stress tensor. It's very easy here using MATLAB. We want to call it V, eigenvector. Maybe it is the eigenvalues first. Okay. So let's see that. How do we get it? Eigenvalues. It is the eigenvalues first. Let us second. Just use the command eig in your MATLAB, and you will directly get what are the okay. So it is reverse. The values should be second and vectors here. Okay. So you can see here, these are the principal stress values. What you see here as 198 as sigma 1, sigma 2 is 67, and sigma 3 is minus 24. So these are the principal stress values, and the directions are given by the columns here. So if I want the direction instead of theta, what I will use is the eigenvector directions to point to the direction of particular eigen principal stress. Okay, so let's see the example here. So how do I get, for example, if I take the sigma 3 value, which is the lowest value, minus 24.13 megapascals, and I want the direction corresponding to this principal stress. I take the first column and write the direction. Direction here will be 0.6086 I with respect to the original x-axis direction minus 0.7656 J and 0.2087 K. So this will be the direction of the principal stress in 3D. In 3D, it is easier to represent the direction with IJK values and components rather than represent the direction with some angles. Okay. So is this point clear? Did you guys understand?
Yes, Doctor. In the exam, we will use MATLAB or not?
Okay, so in exams, I'm not going to give any 3D problem. If I give you a 3D problem, it will be slightly different format. Okay, so that I will show you an example right here. But did you understand this, how to get directions and principal stresses? In your assignment, if I give you a 3D problem, you will use MATLAB to solve it and provide the answer. Okay?
Okay. It is easy in MATLAB.
Okay. You can do the assignment values using MATLAB if it is 3D. But in exams, I will give you a 3D problem, but not a full 3D problem. So what kind of a 3D problem you are going to get? This is how you will get. I will specify some values for sigma xx, yy, and even for zz, like this. And I might give you some values here. Let's say 0, 0 here. And 0, 0. So if you take a look at this problem, it is essentially a 3D problem, but it is very easy to reduce it to a 2D problem. Why is that the case? If you observe here, the shear stress components corresponding to sigma xx values, they are all 0. Okay, when that is the case, it's very easy to reduce this to a 2D problem, and we can simply eliminate the first row and the column and consider only these 4 values as a 2D problem and solve it. Why? Because here, since the shear stress values are 0 here, it implies that one of the principal stresses is along x direction, and we have the principal stress value as 10. Okay, so this becomes one of the principal stress values. However, we have to get the other 2 principal stress values. How do we get it? We reduce it to a 2D problem and then get it along y and z direction. Okay. Now you can solve this problem using the formulas which we have seen for the 2D problem. Apply these formulas to be exact, and in the yz, with respect to y and z axis, we can get what are the principal stresses and the directions also. So you can substitute here. Only thing is instead of having x and y values, you will have y and z values. So substitute here. We are going to get y prime, y prime. Remember, the formula becomes, since it is y and z, we are first calculating sigma y prime with the positive quantity. So substitute here minus 25 plus the should be y prime and z prime, sorry, yy and zz. Okay, so since it is negative, we substitute minus 30 here. Minus 25 minus 30 divided by 2. And we have, remember, we want the positive quantity to be y prime, and square root, substitute here. Minus 25 minus 30 divided by 2 whole square plus 30 square. So that will give you, you can find the value by yourself. Y prime is this value. And similarly, z prime will be the other value, negative of plus 30 square. And with respect to YZ axis, you can find the angle phi. Okay, so if I look from the negative x direction, this is what I'm going to see: y axis and the z axis. Okay, if you don't understand here, you can simply draw a small XYZ directions. Here I'm looking from the negative x direction. In this direction, I'm going to see y axis going up, z coming towards the negative side, and that is what I have drawn. And with respect to the y axis, you get the angle. Okay, so the new principal direction is going to be in this direction, in the anti-clockwise, with respect to the y axis. So here, yeah, yes, so y cross z will give you this, and this will be your principal direction. And you will be asked in exam to provide the angle phi p and show it graphically in which direction it is. So you have to understand all these directions properly and then calculate it. So let's calculate phi p. To get the phi p direction, I have to write this formula: 1/2 tan inverse. Inverting this formula, this is what I get: 2 times tau xy. The tau xy value is 30. In the denominator, I have sigma x minus y. Sigma x is negative 25, minus of minus becomes plus 30. So this will be the angle here. And in this case, you might get a positive or a negative value. If it is a positive value, it is in the anti-clockwise direction. But if you get the negative value here, then it will be in the clockwise direction. Okay, so the negative value of the angle just simply means it is in the clockwise direction. Okay, so this way you can figure out what are the principal stresses and directions only in the YZ plane. Now you will have 3 different values. We have
Doctor,
the
uh,
yeah.
I get the angle 42.6. Does that mean it will be in clockwise?
What do you get?
42.6.
Is it positive or negative?
Positive.
Positive. Okay, so 42.6 degrees, is it?
Yes.
Okay, so assuming this is right, let's just check it out. Just a moment, 1/2. Let's 8 degrees, and then 60 over 60 over 30 minus 25 is 5. Yes, so 42.661 or 42.6 degrees. Okay, so that's right. So this is in the anti-clockwise direction. Since it is positive, it is in the anti-clockwise direction, and this is okay. But if you get a negative value, then it will go in the clockwise direction. Now the direction, which direction of the angle is positive or negative, depends upon how you draw the y and z axis. Be very, very careful. If you have the y axis here and the z axis up here, then it will be anti-clockwise. But if you let's assume this is the y axis and this is the z axis, then clockwise will be positive. So you need to know which one is positive or negative. How do you figure out in 3D whether an angle is positive or negative, which direction is positive or negative? Based upon your right hand rule on 3D axis. Okay, so point your four fingers in particular direction of rotation and see whether the thumb direction is along positive x-axis, y-axis or z-axis. If it is along positive axis, then the angle is positive. If your thumb points towards the negative axis, then the angles will be negative. Okay, in 3D. So that is what we are using here. Okay. Now we need to be careful. If I ask you to draw, or if I ask you to find out what is the maximum principal axis, what is the maximum principal value, principal stress value, and the direction corresponding to the maximum principal stress. For that, we need to find the values here. Have any of you guys found the values here? So if you haven't found out, so let's see here. We have 30, 40, 50, 55 over 2. I just want to figure out the values so we will know exactly how to do this. First, I'm going to find what is R. Okay. Value. So that
The first one is
what?
827.85.
Which one?
The first one. YY.
800.
Minus 800.
I'm doubtful. Just say, did you use the square root here?
Yes.
Okay, so let's see, 3900. Yes. So no, actually, let's see. Let's calculate the R value. Yes, square root 30 square. Cannot get that high value. Here we have 5 over 2 whole square. So 2.5 square. Get 30.1040. Okay, this is the R value. And here what do we have? 55 over 2. So negative 55 over 2. Negative 55 over 2 plus 30.104. Okay. So we have sigma y prime, the principal direction, the principal stress value. We have, what is that? 30, 40, 55 over 2. Negative 5 over 2 plus R value. We get 2.604. You? Let's
Yes,
assume.
yes, Doctor. I put
Yeah,
it
I think you didn't
multiply
take the
instead of
square root, right?
no, I put multiply between them instead of
Multiplied. Okay, so that's why it's too high. So we can check the other value, and this will be minus r, minus 57.604. Okay, let's assume all the units are megapascal. Remember, we already had x prime in the principal stress direction is same as sigma xx value, which is 10 megapascal. Now, in this case, we arrange it in the order and we get the highest value is 10 megapascal, so that is sigma 1. The lowest value is minus 57, so this becomes sigma 3. And the intermediate value is the sigma 2 value. Okay. Now, what is the maximum principal stress direction now? From here, the maximum value is 10 here. That means what is the maximum principal stress direction? Simply x-axis direction. Corresponding to this maximum principal stress is x-axis direction. You will not provide, this is the final answer. You will not give me this angle as the maximum principal stress direction. You have to compare all the three values and then make a decision, which is the maximum principal stress direction. Okay, so for this problem, this is what we get. Sometimes the maximum principal stress direction can be in the YZ axis, and then you will provide the corresponding direction. We also have to see what is the maximum shear stress. We will try to solve a problem. First, we will derive the equations for maximum shear stress in next class. We will solve a problem like this and try to figure out what is the direction. Okay. Okay. So, any doubt up till this point?
Doctor, how we know the maximum direction? Which one is the maximum direction?
You will select which is the maximum value first, principal stress value. In our case, this is the maximum principal stress value. But we already know this value is along the x direction. Why? Because we already found that, right? This is one of the principal stress values.
Yes, Doctor, I ask how we know it maximum.
How you know this? Look, compare here. Which is the maximum
Okay,
value?
the highest one is okay.
The
The highest
highest one.
number.
Maximum means greatest value, right?
Yes, Doctor.
So 10 is the highest value. The lowest value is minus 57. That's all.
Okay.
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 So in this case, if I ask you to draw and show me the stress element along the maximum principal stress direction, how will you show that? In 3D, how are you going to show that? Since it is along the x direction, you will draw two squares. Okay. So for example, here we draw the x-axis, the original x-axis, y-axis. Okay. And then you will draw a square element and then show the original values. But once you have the principal stress values, okay, now this is the original guy. If you see here, 10, right, along this 10 megapascal, and then along the y direction you have minus 25, just in 2D case. Okay, so this you will draw minus 25. But the shear stress in these two directions are 0. No shear stress is 0, 0 in the original one. But if I want it in the maximum principal stress direction, it will be slightly different. We'll finish this and we can leave. Okay. So here, this is the x direction. But now when you draw the y-axis, okay, the y-axis won't be your original y-axis. Rather, we want to draw in the direction of y prime axis. Where is the y prime axis? The green axis here. This becomes your y prime axis. Remember that. The z prime will be 90 degrees to that in the anti-clockwise direction. It doesn't matter. The y prime axis will always be perpendicular to x prime axis because it's a 3D problem. We can still represent this as the y prime axis. Okay. Now the only thing you need to recognize is how to draw the stress element. The stress element in this direction is 10, same 10 along the x-axis. But what is the y prime value? 2.604, and it is positive along the principal stress. Okay. So when you draw it very carefully. You have to look at the problem from 3D orientation. Although it looks like the y and y prime axis in 2D is directed along in the same way, but actually we are looking at a different plane. The xy plane is different from xy prime plane. If you look from the 3D point of view, remember the x-axis is coming out of the board here. Okay, from the origin towards your face, that is the x-axis. So the xy plane, you can see it is this vertical plane, but the xy prime plane is the slanted plane here, represented by the line. Is that clear? Is it clear?
Yes, sir.
Yes,
Okay.
indeed.
Okay. All right. So you need to carefully give the directions. So in 3D, you need a little bit of imagination, visualization to obtain the planes and directions differently. Okay. Okay. So I'm going to stop right here. Next class, we will discuss about maximum shear stress and shear stress direction, especially in 2D, and we will also go for 3D case. We will extend this problem for maximum shear stress as well. Okay. All right. Also, you can try to solve the same problem as a 3D problem by entering into the MATLAB. We will do that next class as well. Using eigenvalues and eigenvectors, you are going to see we get the same results as we get here. Exactly same results we are going to get. Okay. So I will discuss this next class. So see you guys, and I will meet you on Tuesday.
Okay, thank you, Doctor.
Yeah.